In the previous lecture, we have discussed the Einstein's A and B coefficient in very detail, and you have also seen the possibility of amplification. Now, today we are going to discuss a very important concept, and this is regarding the necessary condition for light amplification. Actually, you will see that the necessary condition for light amplification is a particular process, and that is called population inversion. So this population inversion is actually the necessary condition for laser action, you can say, and we will discuss this fact in this lecture just in a qualitative way. It means we will not do any calculation, but in the forthcoming lecture, just after this lecture, we will see the quantitative approach to deal with the same problem. So in this lecture, we will see only in a qualitative way what is the necessary condition for laser action, or what is this population inversion, and how this population inversion is achieved. Actually, population inversion is a very basic or necessary condition for the action of laser, and any laser device we always have a system to get the population inversion. So this is the basic theory of any laser system. And for this, let us consider an assembly of atoms, or you can say an active medium, and these atoms are supposed to be distributed in different energy levels as I have shown in this figure. Actually, these horizontal lines which I have drawn here actually represent the different energy levels, and this small spheres over the line represent the atoms present in that energy level. So in general, in an atomic system or in an active medium means the medium from which you get the laser light is have actually the discrete energy levels. Okay. Now we consider that an electromagnetic radiation, or a beam of electromagnetic radiation, you can say, consisting of a frequency nu, is incident on this active medium or this atomic system. Now you know, if this incident frequency nu match with the frequency just required to just equal to the difference of any two energy level, that is actually called the characteristic frequency. So if we consider that there are two energy levels, E2 is the energy of higher energy level and E1 is the energy of lower energy level, and if this nu is equal to E2 minus E1 divided by H, actually then you say that this frequency nu coincides with one of the characteristic frequencies of this atomic system. In fact, in this condition, when this matching condition will be satisfied, actually there may be two processes, or you can say that this photon, which is actually called a stimulating photon, that will interact with this atomic system in two ways. And what are those two ways? You have already learned in the previous lecture. Actually, in first way, you can say that there may be a stimulated absorption of this photon. When you say a stimulated absorption, what does it mean? It means the atom in the lower energy level absorbs this photon, and this raised to the higher energy level. Let us say that the atom present in this energy level E1 absorbs this photon, and this atom goes to the higher energy level E2. So the incident photon get lost. Okay. So if there are a number of photons striking this system, and all of those are absorbed by the atoms present in the lower energy level, then in course of time the number of the absorbed photons actually increases, and the beam after interaction with the atoms will be attenuated. Its intensity will decrease because the incident photons are getting absorbed. So we can say that finally the intensity of the beam emerging from this active medium will be very small, or you can say that the intensity of the beam striking this atomic system will go decreasing and decreasing continuously, and finally the energy will become zero, or you can say that the beam will actually totally attenuated. Okay. So when this stimulated absorption will take place, finally we get a very less energetic, a very less intense beam, or you can also say that if all of the photons will get absorbed, then we will get no beam emerging from the that active medium. Now, at the same time, you have also learned that if the atoms are present in the higher energy level, as in this figure you can see, I have shown that atoms are present in this higher energy level, that is nth level, or this third level as I have marked here, and the striking photon interacts with the atoms present in the higher energy level. Then you know this striking photon is not absorbed. When the interaction takes place between the striking photon and the atoms in the higher energy level, then actually the striking photon, which is actually called a stimulating photon, are not absorbed, but they only stimulate the atoms present in the higher energy level to go to the lower energy level. And at the same time, a fresh photon is produced due to that transition. If you consider that there is a transition, let us say, from this energy level E2 to the energy level E1, due to the interaction with this photon of energy h nu. Then after this transition from level 2 to level 1, you know a fresh photon is produced whose energy is also equal to h nu. And this striking photon, that is the stimulating photon, remains unmodified. Its energy remains same. So now there are two photons moving strictly in the same direction. You also know, you have studied earlier, that these two photons move in same direction, they have same energy, they have same phase, they are perfectly coherent to one another. They have also same state of polarization. You have studied earlier in a stimulated emission. Okay. Now, these two photons which are now moving in the same direction will now excite the two atoms in the higher energy level. And after the de-excitation of the atoms present in the higher energy level, again we will get two new fresh photons. Okay. So now as a whole there will be 4 photons. You can see this figure. By the interaction of this single photon, we have obtained, we get actually 2 photons. I have marked it here. And due to the stimulation of these 2 photons, now extra 2 fresh photons are produced, and all these 4 photons have same energy, same direction of motion, and same state of polarization. Okay. In the similar manner, you can now say that these 4 photons will excite more 4 atoms in the higher energy state, and those 4 atoms will de-excite to the lower energy level, and again 4 new photons will be produced. So now as a whole, how many photons are in this beam? Now there will be 8 beams. You can see it here. I have marked this by here, that these 8 photons are moving in the same direction. So in the similar way, you can say that when these 8 photons will de-excite the atoms in the higher energy level, now there will be 16 photons moving in the same direction with same energy, same intensity, same state of polarization. So in fact, a strictly coherent beam of high intensity will be obtained. Okay. So when this stimulated emission will take place, then we get a highly intense beam, and that beam is actually called laser beam. Okay. So what you have learned, if you want you have a purpose to obtain a highly intense beam, or you have to obtain the laser light, definitely this stimulated emission must dominate over the stimulated absorption. Stimulated emission should be dominating over the stimulated absorption. Only then we will get the most intense beam or highly amplified beam. So this is the necessary condition for getting the highly amplified light beam or the laser light, and for that stimulated emission should be dominate over the stimulated absorption. Okay. And how actually this will take place? How you can say that this stimulated emission will dominate over the stimulated absorption? Actually, this will only take when there will be a particular phenomenon that is called population inversion. When population inversion will take place, only then the stimulated emission will dominate over the stimulated absorption. How we will learn now this fact. In fact, if our system, atomic system, is in thermal equilibrium at a particular temperature, let us say T, actually the atoms distributed in the different energy levels obeys the Maxwellian distribution law of energy. So you can say that the number of atoms present in the energy level E1 is equal to N1 equal to N0 e to the power minus E1 divided by KT, where K is Boltzmann constant, This is actually the Maxwell's energy distribution law. And at the same time, the number of atoms present in the higher energy level, that is the energy level E2, is given as N0 e to the power minus E2 over KT. Or we simply say that number present in any energy level is directly proportional to the Boltzmann factor e to the power minus E by KT. This is Maxwellian distribution of energy. Okay. So we will see that in normal condition, actually the number of atoms present in the lower energy level, which is N1, will be greater than N2. How you can say that N1 will be greater than N2? Let us see it here. For this, let us find the ratio N1 by N2. You can see that N1 is equal to N0 e to the power minus E1 by KT, and N2 is N0 e to the power minus E2 by KT. Now this N0 and N0 will cancel out, and your result will be what? When you will take this denominator in numerator, this will be e to the power minus E2 minus E1 over KT. Now as you know that E2 is greater than E1, so E2 minus E1 will be positive, and if e to the power x, where x is actually a positive number, this is 1 plus x square over factorial 2 plus so on. So you can say that if x is positive, definitely this e to the power x is greater than 1. And if x is a large number, then this e to the power x will be much greater than 1. Actually here, this E2 is much greater than E1. So in fact, in this condition, we can say that this ratio of N1 and N2 will be much greater than 1. Okay. So in normal condition, you have seen that the number of, or you can say that the population of the lower energy level is larger than the population of the higher energy level. Okay. Or in other words, you can say that this N2 will be less than N1 in normal condition. Okay. And if N2 is less than N1, then stimulated emission will be less than the stimulated absorption, because atoms present in the lower level is greater than the atoms present in the higher energy level. So the chance or the probability of getting absorption of the stimulating photon will be greater. So in normal condition, the stimulated absorption will dominate over the stimulated emission. So if your aim is to promote the stimulated emission, or you have to achieve a condition so that the stimulated emission will dominate over the stimulated absorption, for that we must have to achieve a condition that N2 should be greater than N1. Although in normal condition, you have seen, according to Maxwell's distribution law, N2 is less than N1. But if our aim is to achieve a condition that the stimulated emission is much more probable than the stimulated absorption, for that definitely we have to achieve a condition in which N2 should be greater than N1. As in normal condition, N2 is less than N1, but we are going to achieve a condition in which N2 will be greater than N1. So this phenomenon is called population inversion. Population has been just inverted. It means the level in which the population was less, now it will become larger. So this is called population inversion. So if your aim is to promote the stimulated emission, you have to achieve a condition in which this population inversion has been taken place, that is N2 is greater than N1. Okay. So we simply say that the population inversion is the necessary and sufficient condition for laser action, or to get an amplified beam of light. This population inversion is the necessary condition. Okay. So in one sentence you can say that if your aim is to get a highly amplified laser beam, then population inversion is a must condition. It means the number of atoms or the density of atoms or the number of atoms per unit volume in the higher energy level should be greater than the number of atoms present in the lower energy level. Although in normal condition situation is just reverse, but we have to achieve it. So how we can achieve such a condition? Actually, the process by virtue of which you can achieve this condition, that N2 is greater than N1, that is population has been inverted, that process by which we obtain this condition, that is called pumping. It means pumping is the process by virtue of which one can obtain the condition of population inversion. It means after the pumping process, N2 will become greater than N1. Actually, when we will study the different laser system, then you will see the different type of pumping system is utilized actually in the different type of laser system. Here I have mentioned some of the important pumping process used in different lasers. Only I have mentioned, but the detail will be discussed when we will actually study the particular type of laser system. So I have mentioned here only the four important pumping system. The first one is called optical pumping. Optical pumping means light pumping, pumping by light. Actually in this case, the atoms are excited by a strong light source. You can say a flash lamp or a arc lamp. Flash lamp or arc lamp. Actually when you will study the first solid state laser, which is called ruby laser, then you will see that this optical pumping system is used in ruby laser. You will see later on. When we will study separately the ruby laser, then you will see. Okay. The another important pumping system or process is electrical pumping. In fact, in this condition, the electrons are in fact, in this condition, the atoms are excited by the electronic impact. Actually, electron gets collide to the atom and imparts energy to the atom in lower energy level, and that atoms are excited to the higher energy level, and we achieve the condition N2 greater than N1. So this is called electrical pumping. When we will study the helium-neon laser, the first gas laser, which is called helium-neon laser, then you will see that in helium-neon laser, we utilize this pumping system, that is electrical pumping. Okay. Similarly, there is another pumping system which is called chemical pumping, and this in this chemical pumping process, actually atoms are excited by chemical reaction. Okay. And the fourth one is gas dynamic pumping, and in this case excitation by supersonic gas expansion is achieved. Okay. So you have seen till now in a qualitative way that if our aim is to achieve achieve the highly amplified beam of light, then there must be a population inversion, that is the atomic system must consist of larger number of atoms per unit volume in the higher atomic energy level than the lower energy level. Only then the stimulated emission will dominate over the absorption, and we will get the highly amplified laser light. Okay. But to promote this stimulated emission, there is another technique too, and that is also utilized in all of the laser system. Actually, apart from this pumping system, we also enclose our lasing medium between two mirrors. That mirror may be a plane mirror or a concave mirror, and in this between these two mirrors our lasing medium is placed. Actually, this is called optical resonator. Lasing medium. This is lasing medium. Okay. In fact, in this condition, we encourage the stimulated emission by increasing the density, spectral density of the incident radiation. How we can increase the spectral density? Actually, this lasing medium is placed between two mirrors, and as you know, when the atoms will de-excite from the higher energy level to lower energy level, then you know that a fresh photon is obtained, and this number of photon get multiplied in geometric progression or in exponential manner. And actually, if you place the lasing medium between two mirrors, then these photons are actually reflected. Let us say these are the photons incident on this mirror, and then it will get reflected. And when it will reflected, then again it will stimulate the atoms present in the higher energy level, and they will de-excite to the lower energy level, and again the fresh photon will obtain. So in this way, placing the lasing medium inside an optical resonator, we can increase the spectral energy density you knew of the radiation. So in fact, in an optical resonator, I have mentioned it here, you can see that the radiation repeatedly travels back and forth, and the photons passing through the atoms go on multiplying by repeated stimulated emission. Okay, and in this way a strong coherent beam of light emerges from the system. Actually, after when the intensity of light beam becomes very large, then one of the mirrors is actually partially silvered, and from that is actually called Brister's window, and from that Brister's window the laser light comes out. Okay, so just you have seen in this lecture that what is the necessary condition for getting laser light or getting a highly amplified light beam in a qualitative way. And as I have told you earlier that we will see the same thing, we will discuss the same thing in a quantitative way in the next lecture. In fact, by appropriate calculation, we will discuss these things. Okay, so the main fact of this lecture was what? If your aim is to obtain a highly amplified beam, then you have to achieve the condition N2 greater than N1. In fact, in normal condition, N2 is less than N1, but if by some means we obtain the condition N2 greater than N1, then it is called population inversion, and that population inversion is achieved by the pumping system or pumping process. And when this population inversion takes place, then the number density of the atoms in the higher energy level is greater, and the stimulated emission is actually promoted. It dominates over the absorption. And for further encouragement of the stimulating radiation, we increase the radiation density too, and this is achieved by enclosing the emitted radiation in a cavity between two parallel reflectors, and the radiation repeatedly back and forth, and photons passing through the atoms go on multiplying by repeated stimulated emission, and hence we get a strong and a strictly coherent beam of light which emerges from the system, and that is actually called the laser light. Okay, so I think we have understand this elementary fact, but this is a very fundamental fact which is needed for the study of any laser system. So as I have told you earlier that the same problem will be discussed in the next lecture too, but that will be discussed on analytical basis, that is on the basis of mathematical calculation. Okay.